Hey, Valentine's Day special. What's going on, everyone? Hanging out, enjoying some nice AP calculus problems, I'm sure. Go ahead and get the iPad pumping up. Yeah, so what's going on? Got some chapter 5 to review. You know, good old chapter 5. Got some good stuff in chapter 5, some good stuff. Some integration, some fundamental theorem of calculus. I mean, I'm a little biased, but it's my favorite section in all of calculus. It's pretty exciting. So yeah, we got two people popping off in the chat. Hello, Calc time, Jackson. How you doing, Jackson? Having a good night? Excited to be here. I hope. I'm having a good night myself. Went out to dinner with the family. It was nice. Went to Uncle Tony's. It's delicious. It's good. Good food. It's not it's not like Eli's Kitchen good. Eli's Kitchen obviously my favorite, but it's pretty good. Hey Trevor, how you doing? Jackson, glad to see you're having a good night. Glad to also see that we have some audio working. We have no latency issues. It looks as though we're good. Different view today. Yeah, I actually rotated my desk. I would take the webcam off my computer, but I don't feel like remounting it. But essentially, I rotated my desk so that I'm closer to the window. So it's nice to hang out, do work, and play video games while my window's right there. It's just kind of nice, rotated view. Cool. Glad to see you're doing well as well, Trevor. Exciting stuff. Fun. Well, let's go ahead and jump in. I know a lot of my viewers lately have been catching the stream afterwards. So let us get started. Okay, let's install later. Install this app later. It's asking me to update my Logitech software, and I do not want to do that right now. And we're going to do this. Cool. And I've got me down here chilling at the bottom of my calculator screen, which I think is probably a safe bet. Like the numbers right there. We don't really need my calc for a while. I'm actually just going to go like this. And I'll put myself over here. Yeah. We'll bring the chat back up, and I think we're ready to go. What kind of games? Lately, it's been a lot of new World of Warcraft patch came out. It's very fun. The Call of Duty Modern Warfare, though, just patched like 64 gigs. It's very exciting as to what they're going to be releasing, but it could be Battle Royale. And if Call of Duty releases their Battle Royale, it's going to be very fun. So that's pretty much what I've been doing lately. Anywho, let's go ahead and take a look at Chapter 5. So Chapter 5 live review, I'm doing something a little different this time. After talking to you guys in class, what I'm going to do is a couple days before my live review, I'm going to send a remind out, basically asking what is it that you guys would like to review. And I took those ideas. I had a bunch of people message me, and I tried to weave them into my live review tonight. So we'll do that. I've got about 45 minutes of material planned. It may go a little bit longer, but we'll try to wrap it up around 45 minutes. And then I'll have some time for Q&A in case anyone watching live in the chat has some additional questions they can ask, and we can certainly have a conversation about that. Okie dokie, let's jump in. Per request, the first thing that I was asked for was a topic list, and so here we go. First thing we're going to do is estimate area under curves using LRAM, RRAM, MRAM, and the trapezoidal approximation, so be sure you know how to do that. The second thing is translating old notation to new integration notation, just making sure your variable, whatever it is, like m of c sub k or something like that, just becomes x. Very easy process, nothing crazy. Know the difference between integration and total area. The biggest difference is the integration obviously uses the integral symbol right there. But when I ask for total area, it will explicitly say find the total area. So just look for that, okay? Know your integration rules in section 5.3, and I actually have those rules later on in this live review. Take the derivative of an integral using the fundamental theorem of calculus part 1. So that's when you take the upper bound, you plug it into the function, and you multiply by the derivative of your upper bound, okay? And then number 2, calculate an integral algebraically. That's the fundamental theorem part 2. It's just when you do your antiderivative evaluated at your upper bound minus your antiderivative evaluated at your lower bound, okay? And the last is to express a function in terms of an integral, which is really that big application of the FTC. Chat's popping off. Does integrating the absolute value of a function yield total area? Yeah, so total area is always going to be, so we'll just kind of write this down. The total area is equal to the integral of the absolute value of your function. Okay, and that's just a fact. You can always use that. However, the difficulty will be that a lot of times when I ask you for total area, it will likely be on the no calculator section of the test. So obviously it's not much good to do that because you don't want to integrate an absolute value by hand. It's messy work. You'd have to split the function into two pieces, and nobody wants to do that. Cool. Let's go ahead and take a look. I tried to gather all the formulas and properties of integrals and kind of put them together. So here's the first one at the top, very important. Remember that the integral is basically all the area above minus all the area below. And so integrals are allowed to be negative because if you have more area below the x-axis than you do above, of course, you have a negative region right there, so you would have a negative answer. But total area always has to be positive because it's taking all that negative area, if any, and reflecting it above the x-axis and then finding the answer there. So just make sure you know integrals are okay to be negative. The second theorem, theorem 2, is to take the integral of a constant. All you do is you take the constant value, whatever it is, like 5, and you multiply by the difference of your bounds. And this was very easily proven in the 5.2 video, I think it was, when I showed you just calculating the area of a rectangle. It's a very simple formula there, okay? All right. Here's some more properties. I'm going to zoom in a bit on these. So the first one is the order of integration. Remember, if you have upside down bounds, you can flip-flop them. You pull a negative out of the integral there, okay? 0, the integral from a to a, so one constant to itself, the integral is always 0. Basically, you've accumulated no area from one number to that same number, okay? Constant multiple rule, if you have a constant times a function inside an integral, you can always just take that constant and bring it outside of the integral, multiply by it later, okay? Sum and difference, if you're adding integrals, you can actually just split this up into two separate integrals. This particular rule is very heavily featured in those in and out problems. So a lot of times the AP or the College Board solution guide likes to express their answers like this, where they kind of have like the integral from one function, the in minus the out function. I'm a big fan of doing them separate, like the in function and then minus the out function. Even though they may have the same bounds of integration, I'm more comfortable kind of doing the start plus the in minus the out. So just a thought, you can do whatever you want. If you want to integrate it just one time on your calculator, then just integrate it one time. Additivity, very popular, is when you have like the integral from a to b and then from b to c. It's just the same thing as the integral from a to c instead of adding those two pieces together. Max-min inequality and domination, they don't really come up a whole lot in questions. It's more just like facts that are important to know. For example, you know that let me talk again. I'm trying to say interval inequality at the same time. So you know an integral has a ceiling and a floor. It has a high and a low. And this is because if you have some function that has a max and a min, then the area underneath the curve is at most whatever the area under it at that max is, and at least at the area under the minimum value. So basically, integrals are bounded, okay? Integrals have bounds. As long as your function has a max and a min, then the integral can only go so high or so low. So that's really, max and min inequality itself is whatever the maximum or minimum value is multiplied by b minus a, which is just the integral of that constant, then that's the highest or the lowest the integral could ever be. And domination is really just, again, more logical. Doesn't come up too often in questions. It basically states if you have some function that's always greater than another function, its integral will always be greater, which makes sense, right? If you have a larger function, that larger function has more area below it, and so therefore its integral will always be greater. And this argument can be said, for the flip side of a negative value. If you have a function that's always less, then you have an integral that will always be less. All right, so 6 and 7, they don't come up too often in questions. They're more just facts that you need to kind of consider, make sense of as you move forward. Especially the max-min inequality, really thinking about how to find the maximum and the minimum in those FRQ problems, because that comes up all the time. Okay. Hey, those of you just joining, how you doing? I hope everyone's having a good night. Gonna check the phone, make sure there's no complaints. We are good. Hold on a sec. Valentine's Day crown. Now we're good. Okay. As my daughters, don't tell her I'm wearing it. She'll actually be really upset with me. Next two, obviously, the most important in this entire, I'm actually going to take this off. I can't do it. Sorry. Most important theorems in the section, fundamental theorem of calculus, part 1 and part 2. Part 1 is the derivative of an integral is the function itself. Make sure you multiply by the derivative of the upper bound. I'm just going to write it out. Derivative of upper bound. Okay? Very important when you're doing the part 1, you will multiply by that derivative of the upper bound. Okay, I call that the Jackson-Castell coefficient. All right, because in class I forgot to do that one time, and I've just always called it that. And then part 2, of course, is just how to integrate a function by hand using antiderivatives. Capital F of x is known as the antiderivative. What you do is you take the antiderivative at the upper bound, you minus the antiderivative at the lower bound. Okay? Derivative of the upper bound. Can't forget it if it's named after me. That's right, Jackson. Okay. The last one is the mean value or the average value, known as both of them. And it's very important, you guys, don't confuse this with average rate of change, okay? Think about mean value or average value as just finding the average of something, right? You'd add up all the values and divide by the quantity. That's exactly what average value is for integrals. You just take your integral region, you take the value, right? And then you divide it by the number of spaces it spanned, b minus a. So that's all average value is. It's just the integral, whatever the area is, divided by b minus a, which is the span of the integral. Average rate of change, as you guys know, is just simply y2 minus y1 over x2 minus x1. Okay? So don't confuse those two concepts. I think I gave you an FRQ. It was the group quiz one, I think. That actually had both questions in a single FRQ just to compare and contrast. All right? Mean value theorem, electric boogaloo. Nice. Good times. Okay, I think we're ready to try a problem. One of the first questions I was asked to do is, can we do an average value problem? We certainly can. Here it is. It says calculate the average value of the function x cubed plus 1 on the interval -1 to 3. So the formula for average value is 1 over b minus a times the integral from -1 to 3 of x cubed plus 1 dx. Okay? And as we solve this, it's important to understand what I'm doing is actually calculating a y value. The average value is a y value. It's a height value, such that if you drew a rectangle right at that height value, the area under the rectangle would exactly equal the integral. That's what average value is. It's a very fascinating number, okay? So this is 1 over 4, and then I'm going to use the antiderivative of this guy. So the antiderivative of x to the third, I take the power, I add 1 to the power, and I divide by that new power, plus I'm going to do the antiderivative of 1, which of course is just x. And after I take the antiderivative, I shift the bounds to the right, noting that I've already now taken an antiderivative. And then I just have to plug the upper bound in first. So it's going to be 3 to the 4th. What was that? 81 fourths plus 3 minus, now the lower bound gets plugged in. So -1 to the 4th is +1 plus, and that's just going to be -1 actually, -1 here. And then that's it. So then I'm going to just solve it out. So it's going to be 1/4 times. Let's see if I do 81 fourths minus 1/4, that's 80 fourths, right? And that's 20. 80 fourths is 20. And then I'm going to do 3 minus -1 is 4. So I'm just going to write plus 4, which this thing is just to put my equal signs. This thing is just equal to 1/4 of 24, which is 6, I believe. So the average value, the y value, the function value is 6. So if you drew a rectangle right at y equals 6, the rectangle area would exactly equal the integral. Okay, and the integral is 24. Okay, checking the chat. Oh, chat's popping off here. Is average rate of change a function? Well, let me read this again. So is the average rate of change of a function the average value of its integral? It's a loaded question. Is the average rate of change, so y2 minus y1 over x minus 1, of a function the average value of its integral? No, not necessarily, Jackson. They're kind of doing two different things. Average rate of change is just on average, what's your what's your derivative, what's your rate of change. But the average value is just that y value, such you can build a rectangle on it. So I would not say that is true. They are not, the average value is not the function's average value of its integral. Okay. Sorry, the average value of the derivative. Okay, yeah, still not meant to say derivative instead of integral. Got it. Yeah, I think also not the same thing. Yeah, the average value of the derivative. Okay, I think we're getting hung up on words. So the average value is just the integral, and then you divide it by the span. So if you want to consider that to be like an average, you could. It's definitely kind of like an average. So yeah, I guess in a sense, rereading it with the fixed words, you meant to say derivative instead of integral. So it's the average value of the derivative. Yeah, I mean, it's a height. It's a y value. That's what average value is. So it's literally just the integral, right? And then you divide it by the if you go from 4 to 10, it'd be divided by 6 because your region spans 6 units. So it's just finding that moment you can build your rectangle. Okay, so that's what it is. It's a y value such that you can draw your rectangle and the area of the rectangle is equal to the integral. That's what it is. Okay, all right. So let's do some practice problems. I just kind of threw together some random practice problems, starting with this one first. This is a no calc. Whenever you see a function like this, where you have a perfect square minus x squared under a radical, this is a circle. This is a circle. And the reason why it's a circle is because if you take your circle formula, x squared plus y squared equals r squared, and you isolate y, you get y squared equals r squared minus x squared. And then you square root both sides in order to isolate y. You get y equals the square root of r squared minus x squared. And that's exactly what we have here. So this 36 is taking the place of the r squared. So obviously if 36 is r squared, what is the value of the radius? Well, it's just the square root of that. So the radius is 6. And then the x squared is here. And since it's just a regular x squared, it's centered at 0, 0. So we don't have to worry too much about, where is my circle? It's very easy. It's just a radius of 6 centered at the origin. So it just looks like this. This is my circle. But the only part I'm actually concerned with is the part from -6 to 6. So like from here to here. So the question is, what is the area under the curve? Well, that's just the area of a circle, pi r squared, divided by 4, okay? And that's just equal to r, in this case, is 6. So 6 squared is 36. 36 pi divided by 4. What is that? 36 divided by 4 is 9. So just 9 pi. 9 pi would be the area there. That'd be the answer to the integral. Also, you're looking at the integral from -6 to 0. You might think to yourself it's got to be negative, but not necessarily because all of the graph from -6 to 0 is above the x-axis. Okay, checking the chat. Chat is clean. Awesome. Hope everyone's having a nice night or morning or afternoon, whenever you watch this video feed later. Let's try another problem. This one says the integral from 0 to 10 of 3.5 dx. Okay, so this is a constant, all right? And the integral of a constant is the constant value times the difference of your bounds. In this case, the answer is just simply 35. All right, so don't let a question like that trip you up. Integral of a constant is the constant value times the difference of your bounds. Okay, find the area bounded by the curve y equals x cubed minus 2x and the x-axis from -1 to 3. So what we're looking for here, guys, we're finding the area, the total area. So we can't just integrate this thing from -1 to 3. I have to figure out when, if ever, it dips below the x-axis. And in order to do that, the easiest step is to just find its zeros. Okay, so let's find its zeros. So if I factor an x out, I get x squared minus 2. So I get zeros of 0 and plus minus root 2. Okay, so if I were to produce just a quick picture of this thing, here's, actually I'm going to go a little bigger so we can kind of look at it and go a little bigger. So here's 0. Here's negative root 2, and here's positive root 2. And I know from its end behavior, it's a cubic positive leading coefficient, so I know it's going to end up here and end up down here. And I know then it's just going to go woo Great stuff. Something like that. That's just a rough estimate, okay? So if I need to integrate this thing from -1 to 3, I need to figure out where I am. So I know rad 2 is like 1.4, right? So if I integrate from -1, that's going to be a little bit past this moment. So I'm going to start integrating from here, and I'm going to stop integrating at 3, which is going to be like somewhere over here. So make somewhere over here, okay? So the area that I need to find, I need to find the area from here to here, okay, which is going to be, I'll just shade it in, positive area. I need to also find the area from here to here, which is going to be this little negative region, okay, so below the x-axis. And then I need to find the area from here to here, okay, and we'll just shade that in. Look at that, beautiful. If I need to find total area, I need to be sure all 3 of these regions come out positive, okay? So the only one I have to worry about is the purple region. Essentially, I just need to subtract the purple region so that my answer, my integral giving me a negative, is then subtracted, which would in turn give me a positive. Or I could just calculate them all separately, take the absolute value of them, and be in decent shape. Essentially, here's the setup to the problem, okay? The setup to the problem would be that the area is going to equal the integral, so from here to here, so from -1 to 0, of, what's my function? X cubed minus 2x. Now that's going to give me a positive answer because it's above the x-axis, so that's clean, okay? Can we do an average value of the integral problem? Yeah, I'm not sure what you mean, but yeah, we can talk about that, Ari. We'll do some Q&A at the end for sure. So -1 to 0, x cubed minus 2x dx, okay? Good stuff. The purple is the problem, so if I just subtract it, I think we'll be okay. We'll do the integral from 0 to √2 of x cubed minus 2x dx. Now what this is allowing me to do is the purple integral will be negative. So if I subtract it, it'll come out positive. So this is good. This is 2 positive answers here. Plus the other integral is going to be above the x-axis as well. So it'll be √2 to 3 of x cubed minus 2x dx. Okay? This is the answer to the problem, but this is a no-calc question, so I have to do the math out. Let's see if I can do the math out. I'm going to add a page here. Okay, so let's see if we can do this out. All I really have to do is calculate the antiderivative one time. Let's do it. So antiderivative x cubed would be x to the 4th over 4 minus antiderivative 2x is x squared. Evaluated from -1 to 0, and I just calculated it, so I really don't have to do any work anymore. Evaluated from 0 to √2, and then evaluated from √2 to 3. All right, so it's just going to be a little bit of arithmetic, but nothing too crazy. Let's do it out. Okay, top first, 0 goes in, 0 comes out. Minus, bottom. By the way, I like to write the zeros because sometimes I forget the negative in the front because it's, top minus bottom bound. So I like to write the 0. All right, -1 goes in. -1 to the 4th becomes +1/4. Minus -1 squared is +1. Okay, so here's the first piece. So I guess I'll put it in brackets just to be clear. Minus, new bracket, new parenthesis. √2 goes in. √2 to the 4th is 2 times 2. Right, √2 times itself 4 times is √2 squared times √2 squared. That's what I did. So that's just 4. And 2 times 2 is 4. Divided by 4 makes 1. Okay, so √2 to the 4th, 4. Divided by 4 makes 1. Minus x squared, which is just 2. Minus 2, because √2 squared is 2. So that's the top bound. Minus the bottom bound is just 0. So that goes away. Nice. Plus, here we go. 3 goes in. So 3 to the 4th is 81/4. Minus, hold on, water break. I'm not getting sick, but I just feel like I'm getting sick, All right, so √2, oh no, I didn't finish the 3. 81/4 minus 3 squared is 9, okay? Minus √2 goes in. I think I already did that, but √2 to the 4th would be 4/4 is 1, minus √2 squared is 2. Parenthesis, bracket. Okay, we did it. I think I did everything properly. Let's see if we can keep going. Shout out in the chat if there's any mistakes. So the first one's going to be 1/4 minus 1. I'm just going to call it -1/4 plus 1. I noticed an 81/4 again on the right, so I'm not going to bother adding those together, okay? Minus 1 minus 2 is -1, so that's going to turn into plus 1, and then the 0 goes away. Plus, here's my 81/4 minus 9 minus, and then 1 minus 2 is -1, so again, another plus 1. So then I can just add together 81/4 and -1/4 is 80/4, which is 20, plus 1, 2, 3, take away 9 is -6. And I get an answer of 14. I get an answer of 14. Okay, and this is easily checkable. So let's see if I'm just going to check it real quick. We can just minimize my program. Minimize. No. Yeah, there you go. Okay. Move over. Aha! I defeated you. Okay, so let's go here. Let's do. So if I wanted to calculate the answer to this question, I just have to put the original function into absolute value, okay? So this is really just going to be the integral from -1 to 3. Oh, I probably should just do this from the home screen, actually. The integral from -1 to 3. I'm going to do second catalog, absolute value, so enter. And then it's x cubed minus 2x dx. Okay, and hope we get 14. Hoping we do. We do! A little bit of rounding error. That's okay. The calculator is trying its best. I wonder if Desmos gives you a rounding error, actually. I don't think it would. I'm going to choose to just not do it right now. But if you plug that in Desmos, I'm curious if it gave you the same rounding error or if Desmos is a little bit better than the TI. All right, so we did it. We win. We're victorious. A problem like that, a great problem, actually. I'm going to just move me over now. Oops. I'm going to open up my Logitech software. Okay, Mr. Schachter is now on the calc, so I'm not blocking any of the iPad. Okay. All right, we're checking cool background. Thank you. Wait, so is the area bounded integral or total area? Wait, so is the area bounded integral? I'm not sure what that means, Jackson. You rephrase, I'll answer that question, okay? I feel that getting sick, but I'm not sick. Yeah, thanks, Jackson. I just feel like that's like February or January or all of it. I don't know. But sick, but no, I'm not sick. All right. Here's another question for us to try. This says find the total shaded area, and the function here is 3 minus 3x squared. This is no calc, okay? No calc. So I'm just going to leave my calc up for now. We'll just, you know what? We're going to save energy. Save fake energy. Find the total shaded area. Okay, so let's see if we can analyze this thing. From here to here, it looks like it's just a clean integral, right? This region is just the integral from 0 to 1 of 3 minus 3x squared dx. That should be fairly easy to calculate. And then I'm going to switch my color. It looks like this guy is just a rectangle. Its area is just 9. 9 is the base or the width, and the height is whatever. The thickness is, I don't know, whatever you want to call it. Base times height, width, base, length. It's 9. 9 times 1 is 9. Then the other guy is a little bit trickier. The integral exactly would actually give me this region. Oh, it looks horrible with that blue. Sorry. The integral would actually give me this region right here. But the region I want is the region below that. I know, though, that together they add up to 9 because it's a rectangle. So I think I could actually find that area. I'm going to use a pink right here. I think I could actually find this area, okay, by doing 9 minus the integral from 1 to 2 of 3 minus 3x squared dx. But I need to be a little careful because this entire thing is actually going to be below the x-axis, all right? So I think I could get around safely by doing this. So I know that the total area is 9, right? It's very easy to look at that and just say the rectangle is 9. So if I find the absolute value of the integral, then 9 minus whatever that number is will give me the shaded blue region, 9 minus the highlighted region. All right, so I think I can do the math here. Let's go do the red one first. The red one should be pretty easy. I'm going to do it right here. So it's antiderivative of 3 would be 3x minus antiderivative 3x squared would be 3x cubed over 3, which is just going to be x cubed, evaluated from 0 to 1. So that's just the 1 goes in, I get 3 minus 1 is 2, and the 0 just makes 0. So the answer is 2. The little shaded region right there is 2, okay? This one I could go do as well. It's 9 minus, oops, not equals, definitely not equals. 9 minus the integral from 1 to 2. I just did this antiderivative, right? So it's just 3x minus x cubed from 1 to 2. And I have to, whatever this is, I have to take the absolute value of it. So 9 minus, okay. So 2 goes in. So 2 times 3 is 6, minus 2 cubed is 8, minus 1 goes in. So 3 times 1 is 3, minus 1. All of that absolute valued. So 9 minus, okay. 6 minus 8 is negative 2. So absolute value of negative 2 minus 3 minus 1 is 2. Okay, so that's just the 9 minus the absolute value of negative 4, which is 9 minus 4, which is 5. Okay, 5. So get my equals. I'm picky about those equals. I like having those, but I don't write them when I'm rushing. So 5. So this is 5. So the total area would therefore just be the sum of, see if we can get a color that could stand out on that blue, maybe like a white. The sum of that, that, and that. So 9 and 14 and 16. So the total area is equal to 16. Total area is 16. Okay? Check in the chat. Oh, Jackson's back with this question. Sorry, should have been more clear. When it asks for area bounded, should we calculate the total area or the integral? Total area. So I'm going back to the question just to verify, because I just want to make sure we did it right. Find the area bounded by the curve. Yeah, this is the giveaway, Jackson. I think it really wants, whenever it says area or total area, it really wants you to calculate the actual area, as opposed to if I want you to calculate the integral, you will see an integral symbol. Okay, I promise. I'm not going to try to trick you. All right, so if I want you to do the integral, you'll see the integral symbol. I want you to do area. I usually say the word find the area or calculate the total area. Okay, so I got an answer of 16 there. How's that? Pretty good? Pretty good, chat? Checking the backgrounds. Cool. All right, chat is happy. We're moving on to my FRQ. This is the last problem I have prepped for tonight. So we'll burn through this, and then we'll allow some time for some Q&A if people have some other questions, okay? So this one is just a question I pulled. It's really similar to the one from class tonight or earlier today. It says, rocket A has a positive velocity after being launched upward from an initial height of 0 feet at time t equals 0. Okay, that seems to be an initial condition. The velocity of the rocket is recorded for selected values of t from 0 to 80, as shown in the table above. Okay, so velocity is feet per second, and t is in seconds, and it gives me a bunch of values, all right? A, find the average acceleration of rocket A over the time interval between 0 and 80, indicate the units of measure. All right, this shouldn't be too bad. You guys know, whoops, literally just dropped the stylus, happens to the best of us. You guys know that average acceleration, you use the function before it. So if I want to find average acceleration, I'm actually going to find velocity. So if I'm going from 0 to 80, it would be velocity of 80 minus velocity of 0, divide 80 minus 0. Okay, and this is calc active, so I can use my calc. Velocity of 80, I'm just going to use the data table, is 49. Minus velocity of 0 looks like to be 5, minus 5, divided by 80. And that's just going to equal 44 over 80, which I'm going to just use my calc to simplify. Both even. Can divide it by 2. Let's see what the calc says. 0.55, which you guys know, you click math, fraction, enter, and it tells me is 11/20ths. 11/20. It's not that bad. Didn't really need the calc. What's the unit here? Okay, so I did velocity, right? Velocity is in feet per second, according to the table. And I divided feet per second by seconds. So what I have is feet per second, or feet per second squared, a little easier to write it like that. But I really like calling it feet per second. It makes more sense to me, right? What's changing is the feet per second. The rate of change is changing. So I kind of Kind of like calling it feet per second, but that's just me. Okay, part B. Use, my iPad keeps sliding down. It's falling. Let's just hold it right here. Just do some review tonight like that. No, just joshing. Using correct units, explain the meaning of the integral from 10 to 70 of v of t dt in terms of the rocket's flight. Okay, well, this is very simple. I'm integrating velocity. So if I'm integrating velocity, what I'd be calculating is distance or position, right? So if I calculate the velocity from 10 to 70, I'm going to basically get the total distance or the total accumulation of distance of the rocket from t equals 10 seconds to t equals 70 seconds. So the integral from 10 to 70 of v of t dt represents the total distance traveled and you know what it is actually saying using correct units. So I'm going to say like in, what is it, feet? Yeah, it's feet. In feet, because it wants me to use the units, okay? Represents the total distance traveled in feet of rocket A from t equals 10 to t equals 70 seconds. Okay, so I just answered the first part of the question. Second part of the question says, use a midpoint Riemann sum with 3 subintervals of equal length to actually approximate the integral from 10 to 70 of v of t. So I'm going to write the integral from 10 to 70 of v of t is approximately, right? That's the symbol for approximately. Now I'm going to go up and look at my table, okay? So I'm going from 10 to 70. So let's actually, I'm just going to erase this for a bit. And I'm going to go from 10 to 70. And it said to use 3 subintervals, okay? So let's count my data points. I'm basically going from 10 to 70, right? So if I got 70 minus 10, which is 60, divided by 3, tells me each one of these guys has to have a distance or a thickness, a width of 30, okay? So rectangle number 1 is going to exist between 10 and 30. Rectangle number 2 will exist between, we'll do that in a minute. So rectangle number 1 exists between 10 and 30, which means if I need to use a middle, MRAM, I need to pick the average of the endpoints being 10 and 30, so it would be 20. Okay, and that's 22. So I'm going to go and scroll down for a sec. And that's going to be 30 is the thickness times 20. Was it 22? I literally forget it already. Yeah, 22. Okay. We're erasing. I'm going to keep the red, actually. Can I just erase the... Oh, so cool. All right. Rectangle number 2 is now going to exist between, so 0 to 30, then 30 to 60, right? Oh, sorry. Wait, did I just do something wrong? Ha, yeah, I did. Otherwise, it's a good way to catch yourself, huh? Well, rectangles weren't going to be able to fit. It's because 60 divided by 3 is 20, not 30. Okay. Easy fix. No problem at all. This is 20. So let's see. So I'm just going to go here and I'm going to sketch rectangle number 1 is going to exist for basically 20 spaces. So it's going to be from 10 to 30. Ironically, I still picked the right value, even though I did my math wrong above. So 20 times 22 is still correct. Okay. Erase the pink. So then I'm going to go from, the first one exists from 10 to 30, which is 20 spaces, right? So then I'm going to go 30 to 50. Hold on one sec. Sick, but not sick. Nope, not sick. Okay. So the next one, the midpoint would be 40, right? Because the left endpoint is 30, the right is 50, the middle of that is 40. So 35 is the value I want. 35 plus. All right, that rectangle's gone. Here comes the last rectangle. So rectangle 1 from 10 to 30. Rectangle 2 from 30 to 50. Rectangle 3 from 50 to 70. They each span 20 units long, okay? 60 and 44 are the values I want. And 44 is the y value. Here we go. Punch it in a calc. 20 times 22 plus 35 plus 44 equal. Ooh, I gotta do a 44, please. Equals 2000. Whoa, no way. That's this year. That's sick. 2020, baby, 2020. Woo. That's cool. Actually, you know what? I literally just found the best problem I could have given on the new year. I could have given you this exact problem. Find like the integral from 10 to, opportunity missed. 2020. Before we move on, let's just make sure I did the units here. This is the integral of velocity, which of course would represent total feet, 2020 feet. Okay, let's check in the chat. Oh, how you doing, chat? Let's see. Sorry, it should be more. Oh, we read that. Thanks. Wouldn't it be 20 units? Yeah, I totally would, Trevor. Thank you. Sick but not sick. 2020. Awesome. Okay, I like the chat tonight. It's very silly. Popping off. Love it. Okay, we're back now in letter C, the last question in the problem that asks me the following. Rocket B is launched upward with an acceleration of that feet per second, okay? At time t equals 0, the initial height of the rocket is 0, and the initial velocity is 2. All right? I can see where this is going. Which of the two rockets is traveling faster at t equals 80? Interesting. Well, before I do any work with rocket B, I can automatically tell how fast rocket A is going at 80, right? At 80 seconds, rocket A is going 49. So I'm just going to write that down. So part C. Rocket A is traveling at, oh my gosh, I already forgot it. Sometimes I talk too much and forget. 49 feet per second. Rocket B, unfortunately, I don't have velocity. What they gave me was acceleration, right? So the question is, how do I find velocity if I know acceleration? Well, I integrate, of course. I'm going to integrate that. But I have to be careful of the initial condition. The initial condition of the velocity is 2. The velocity is 2 when t equals 0. That's my initial condition, okay? So here we go. Y value of the initial condition, 2. We'll call it velocity of rocket B is equal to plus the integral from the x value of the initial condition to the variable. I'm going to use a t, and I'm going to go scoop up the velocity, 3 over root t plus 1, 3 over root, and I'll use x plus 1 dx, because if I use an s, I think it'd be a 5. I'd confuse myself, so I just like using the x. Okay, so I need to find out at t equals 8. Okay, so velocity at 8 is 2 plus the integral from 0 to 8 of 3 over the square root of x plus 1 dx. And this is going to equal, here we go, Calc-E, my trusty assistant, 2 plus math 9, 0, up, 8 over 3, divide, no. Yeah, actually it's okay. Radical, x plus 1. Okay, dx, all right. We're hoping for a number here. We got 14. That cannot be right. Mode. No, it's not a, what's wrong with this? I don't know. It's not the division, right? This isn't going to make a difference. Right? That makes no difference. 14. Yeah. So what's wrong with this? Did I type it in right? 3 over square root of x plus 1? 3 over square root of x plus 1. Oh my gosh, I'm doing it to 80. I am so silly. Look at this. Look at this. This should be an 80. Should be an 80. V of 80. That's right. I was like, there's no way the speed of this rocket after 80 seconds is 14 feet per second. There's no way. Second insert 80. Common sense is really going to serve you well in the future. 808. Nice. Rocket. Good job. We'll try that one more time. Just one more time. It's like I'm integrating from 0 to Bob. Delete. Okay. Here we go. That's a lot better. 50, and we'll call this feet per second. So obviously the question is, that'd be a very slow rocket. Yes, it would indeed. Thank you, Trevor. I should probably look at chat before I start punching away in my calculator. What would I do without you, Trevor? Obviously, rocket B wins just by a hair, just by 1 feet per second. So what does the question actually ask? Like, who's traveling faster? Which of the rockets is traveling faster? Explain. Okay, I can do that. So rocket B is traveling faster than rocket A. And I'm just going to, you know what I'm going to do? I'm going to be lazy and go like this. Watch this. Therefore, my work speaks for itself. Rocket A at t equals 80 seconds. Rocket B's velocity at seconds is 50. So therefore, rocket B is traveling faster than rocket A. All right, I think we've defeated the AP question. Oh, it is exactly 9:15, which means I did well. I planned my 45 minutes, and I used my 45 minutes. Now I am officially open for business. In the chat, anything you guys feel like you would like to maybe ask me, a conversation to have, a problem to look at, the floor is yours for 8 or 15 minutes. 15 minutes. Pull this up too while we're chatting. I just wanted to show you guys. I put the live review problems right here on our guide in case you want to try it. Okay. Oh, Ari had a question too. Actually, I wanted to go back up and read that. Ari, can we do an average value of the integral problem? Oh yeah, Ari, I just needed some clarification as to what you mean. Like average value of an integral. Like, I mean, we did that. Maybe you were streaming a little later. We actually did this problem right here. We calculated the average value of the integral of x cubed plus 1, or of the function x cubed plus 1. Is that what you were referring to, Ari? Just let me know, and we can certainly do something else if you would like to see something else done. All right, I'm still confused on the difference between an integral and an antiderivative. When do we use each? Great, I can certainly help you with that, Jackson. Can you do an in and out problem? Trevor, we definitely can. I'm not sure, to be honest, it's even doable with the time we have left. We could certainly maybe look at one, like a solution of an old one, just kind of dissect it. But let's talk about Jackson's point for a minute. Great question. Integral versus antiderivative. Okay, so essentially an integral, okay, as far as we know, because we only study definite integrals, is some kind of a constant. Okay, it's a number. Specifically, what it represents is the area under the curve of some function. Okay, that's what it represents. Whereas an antiderivative is a function. All right, it's not a number, it's not a value, it has variables in it. It itself has variables in it, okay? And specifically, it's the backwards derivative. That's what an antiderivative is. So if you have like velocity, the antiderivative of velocity would send you back to position, okay? Interestingly enough, the integral itself uses the function's antiderivative in order to calculate it. So that's kind of the cool connection, is in order to calculate an integral using the fundamental theorem part 2, you need the function's antiderivative. And what you do is you plug the upper bound, the upper limit in, and you minus the lower bound, the lower limit. And that's how you calculate an integral. So an integral is a constant, an antiderivative is a function, and they differ by some constant value, because if you evaluate the antiderivative at those values, then you get the actual integral. So they are very, very similar in nature. Jackson, you let me know if that helps you kind of understand it. Integral is area under a curve. Antiderivative is a function whose basically, if you took its derivative, you took this new antiderivative's derivative, you'd end up back at the original function that I gave you. Okay? Okay, in and out problem for Trevor while Jackson is mulling that over. Like I said, we only have like 10 minutes, so I don't really have time to start a fresh one. But, what I could do is pull up. I think in and out was day 1, to be honest. Let's see if we can look at like the first problem we ever did together. It says water is pumped into an underground tank at a constant rate of 8 gallons per minute. Water leaks out of the tank at square root t plus 1 gallons per minute between 0 and 120 minutes. At time 0, there are 30 gallons, okay? So A, how many gallons of water leak out from 0 to 3? Whenever you're solving for the accumulation of something, you have to integrate. Specifically, you can use units to help you. If I need gallons and I'm given a rate of change function, I need to integrate and go backwards, right? So the integral from 0 to 3 of the function gives you 4 2/3 gallons. Now notice I integrated the square root function because that's the function it says that water's leaking out. Water's leaking out, okay? So I wouldn't want to integrate the function of water leaking in, which is going to be, it says 8 gallons per minute. So I wouldn't use that here. Okay, checking the chat. Oh, okay. That was very helpful. So graphing an integral is just graphing the area under a curve at every point. That graph's not exactly the antiderivative. Yeah, they differ by a constant, Jackson. Remember, there are actually, there's a whole family of antiderivatives, right? All these functions who, if you took the derivative of any of them or all of them, they'd actually lead to the same exact derivative, which is kind of cool. So that's why they differ by a constant, some plus C value. Okay, back to in and out. Are you even, oh, okay. I got nervous for a minute. I didn't see my iPad over here. I thought you weren't seeing anything, but we're good. B says how many gallons of water are in the tank at t equals 3. This is your straight up application of your start minus in plus out business right here. Okay. Can you even see my cursor? No, you can't see my cursor. Okay. How do we rectify? Oh, you can't see it. How do we rectify that? We'll just point. Yeah, that doesn't help. You can't see it. All right. Well, you get the idea. It's right here in front of us. Just scooch it down so you can see the whole problem. Okay, so start is, they told you the initial condition is equal to 30 gallons, so 30. And then we subtract the out. So the out we just calculated is actually 4 2/3 gallons, right? And the in, well, it's at a constant rate of 8 gallons per minute. That means every minute another 8 gallons has gone into the tank. So after 3 minutes, 8 times 3 is 24 gallons have added to the tank, so plus 24. That gives you 49 1/3 gallons have actually been in the tank at t equals 3. So that's including the leakage and the flowing in and the 30 gallons in the beginning. Okay? C, write a function for a of t, the total number of gallons. This is like your standard question, right? It's the start minus the in plus the out. So it's 30 minus the integral from 0 to t of square root s plus 1 ds, switch your variable, plus the integral from 0 to t of 8 ds, making sure you know that at the end there, you could have also just said it's 8t. You didn't have to integrate. You could have just said 8t, okay? Quick water break, sick, not sick. Okay. Last but not least, when is the amount of water in the tank a maximum? So very important. Let's just break it down for a minute, AP Calc. Maxes and mins, you have to include the endpoints, okay? That's like anyone that lost points on their FRQs is probably because of that. You didn't check the endpoints. You have to, okay? I'm a big fan of just taking the critical points and the endpoints and finding the actual values and then picking the biggest one or smallest one if you're minimizing. But you can also argue it with area on like graph questions. You can argue it with like positive and negative area canceling out. There's always ways to kind of be logical with it. But this one, it's very simple to actually just calculate a of 0, a of 63, and a of 120. Recall that critical points are from zeros or undefined values of the derivative, okay? So in this case, the derivative of this integral is just equal to negative square root of t plus 1 plus 8. And then therefore you can set that equal to 0, solve for t to get 63. That's how you get the critical point there, okay? Plug in the values in your calc, and the biggest one comes at 63. So therefore it is the maximum, all right? So Trevor, I hope that helps. I know, there's hundreds of in and out problems out there. All you gotta do is just Google old AP exams, try to find one we haven't done yet, and bam, you've got yourself another one to practice. And you guys know too, if you actually Google, I'm gonna put my iPad up for a sec. Checking YouTube, making sure the iPad, oh, that's right, because I have 2 tabs now. There we go. You guys know when there's 2 types of exams actually. So there's like the 2016 AB FRQs. And then they have something called like the 2016 AP/AB SGs. And the SG just stands for the scoring guide. That's how you look at like the answers that they've submitted. All right, so you can just Google old AP exams and look for some in and out problems or some FTC problems. There's usually one every year. Okay. I'm checking the chat. No problem. Happy to help. Whoops. You guys let me know if there's anything else. We got about 5 minutes left. If not, I can tell you how amazing I think Frozen 2 is. Love it. Saw it in theaters. Gonna buy it probably tonight and watch it with the kids tomorrow. Actually, maybe watch it myself tonight, selfishly, and then tomorrow with the kids, but pretend like I hadn't seen it since we saw it in theaters together. Be like, oh, I didn't remember that scene. That's so cool. Yeah, I don't know. It's a good movie. I like it. Good flick. So yeah, we're checking the phone. Make sure no one's like upset at Remind. We are good. Everyone is clean. Never saw Frozen 2. Is it worth it? I think so. I'm a big fan of Idina Menzel. I mean, when she sings, I really think it's like Dax Shepard, actually, Kristen Bell's husband, kind of describes it as a Bruce Lee fight song. When Idina Menzel sings a song, like it like builds up to this like insane finale, and I'm gonna get you all dizzy flipping my iPad so many times, and I think it's worth it. I mean, I love it. I love Kristen Bell. I love Idina Menzel, and I think it's a great movie. So yeah, I would definitely check it out. Haven't seen it yet. No spoilers. No spoiler. No, I didn't say anything. I'm just saying Idina Menzel rocks, and Kristen Bell's awesome, and it's a great movie. So I would definitely check it out. Cool, guys. Thank you for joining me. I hope this was helpful. I like the new system of asking you guys to kind of design some of the topics, and I pull some questions. And then we always have time for a little bit of chat at the end, some Q&A. Okay? I hope you guys have a wonderful night, and I will see you for some more review. Everything is on the planner, so you can access that. You can try these problems fresh again after watching them in the live view if you'd like. Okay? Awesome. All right. Have a wonderful night, guys.